In this video, we are introducing Newton's third law. We're going to look at the definition, which is fairly straightforward, and then we'll see a couple of examples that really go into kind of the twist, because there's sometimes more than meets the eye with the third law in terms of what it says and what it doesn't say. All right, so starting us off, the definition of Newton's third law says when one object exerts a force on a second object, the second object exerts an equal and oppositely directed force on the first object. And I have this diagram here to emphasize. Let's say you're pushing on a wall. Okay, you apply a force on the wall like so. I know the arrows are already drawn down here. The wall, according to Newton's third law, is going to apply an equal and opposite force on to you. That's why, for example, you can't walk through walls. All right, your head hits the wall hits you back in the head. Okay, these forces are always going to be acting in the opposite direction. So if there was a force this way, maybe you're pushing up on the ceiling pushes down on you. If you apply a force that's directed up and to the right, there'll be a force down and to the left, oppositely directed and equal in magnitude. This one was positive 5 newtons. This one would be negative 5 newtons. Same amount of force, just acting in opposite directions. The third law really goes to explain a lot of common things we experience here in the real world. For example, if you're firing a gun, whether in real life or in video games, guns have recoil. The recoil is due to Newton's first law. The gun applies a force on the bullet applies an equal and opposite force on the gun. So the gun is going to move backwards. If you watch, I don't know, some YouTube video of someone failing trying to get off of a boat, okay, they step off of the boat because they want the boat to push them toward the dock, but the person pushes back on the boat itself. So the boat tends to slide backwards and then the poor sucker falls into the water. Rocket ships are based on the third law. This time, the rocket is pushing on the gas and the exhaust. And those particles, the gas particles, the exhaust particles, push back up on the rocket. That's how rockets are able to move in outer space, by applying a force on particles that are being forced out of the rocket. Those particles apply an equal and opposite force back on the rocket ship. Even something as simple as if you take a balloon, you blow it up with air, you let it go, it flies across the room. It's the same thing. This is really what's going on with a rocket. Okay, the air is being forced out of the balloon, so the balloon is being forced up by the air. I will say, because they have it here, don't say action and reaction. All right, you may have heard the third law: for every action there's an equal and opposite reaction. That's a terrible definition, because action and reaction is very unclear. We're talking about forces. And also that classic, for every action there's an equal and opposite reaction, doesn't get into the key idea that these forces are on two different objects, person and wall. Okay, so let's look at an example. I don't think you have to write these down, all right? I would just try it, maybe hit pause and think about the answer and how you would explain it. Obviously, you can write it down if you want, but here's the first example I have for you. A small car, I couldn't actually find a car, so it's a small red truck, crashes into a large truck. And to make matters worse, this large truck is traveling 10 times faster than this red pickup. The question is straightforward. Which experiences a greater force? All right, what do you think? What would be the answer? The correct answer is that they experience the same force. Even though this semi is so much bigger and it's going so much faster compared to this little red pickup, they both experience the same force. To be honest, I was trying to throw you off with this 10 times faster thing. It doesn't matter whether they're both going slow, if they're both going fast, if one is going way faster than the other, they will always feel the same force. Now, where this gets tricky is that if you imagine a crash like this, or let's make it even more extreme. Let's remove the truck. Let's say it's a fly. Can't really draw a fly. Oh gosh, well, that's not happening. So a fly hits the windshield. Which experiences the same force, the fly or the truck? It's still the same. And you think, well, wait a minute, how could it be the same? The fly is going to be dead, right? The fly gets demolished. Or if you think of a small sports car, if it hits a large truck, the sports car gets destroyed. It gets obliterated. But the bigger object, the truck, has very little damage. How could they be experiencing the same force? The damage, whether it's to the fly's life or to a small vehicle, is not really due to the comparison of the two forces. It's about their accelerations, their deceleration. If we think of it in terms of this, the force from this truck is equal by the third law, equal and opposite, to the force on this truck. Well, that truck, if that's the only horizontal force, this one has a huge mass. This one has a comparatively small mass. Well, if the net force equals ma, and these two things have to be equal, if this one has a larger mass, it experiences a smaller deceleration. This one with a smaller mass must experience a larger deceleration. This is why the truck has more damage. It's not the force that's destroying the truck, it's the rapid deceleration, which causes warping and bending and heating and crunching and smashing of the structure for the truck and for the fly. The fly decelerates so rapidly, its back end meets its front end and it's squashed. Okay, the forces are the same. Now, it's true that if maybe they were going much faster, these forces would be larger. I'm not saying the force is always the same for every collision, but if we had a different scenario, I'll switch to red, where the force was small, they're still both small. Or if there is a collision and they experience larger forces, they are both larger forces. There's a difference between them. These forces are always the same compared to each other. Okay? And because their forces are the same, if something has less mass, the one with that smaller mass will have more acceleration. Okay? I have one more example for you. Here's a classic physics conceptual question. We have a horse pulling a cart. Okay, and here's what I have. A lazy horse is pulling a wagon, or it's at least trying to pull a wagon, as shown. The horse thinks. Yes, the horse is thinking. If I try and pull the cart forward, there will be an equal force backwards. It doesn't matter how hard I pull. The third law says there will always be an equal force in the opposite direction. Therefore, I'll never be able to get the cart moving, since the forces will cancel out. There's no point in this horse trying to go anywhere. Anytime they try and apply a force on the cart, there'll be an equal force backwards. They have to cancel out by the second law, really. Therefore, you'll never start going. What's the solution to this? Is the horse right? I'd say hit pause. Again, I don't know if you have to copy it down, but think of how you would respond to this. A lot of students would say something like, oh, well, the horse can pull more than the cart can pull back. But that's absolutely wrong. The third law is crystal clear. When the horse applies a force, the wagon applies a force that is the exact same amount, period. The horse can't pull more on the cart than the cart pulls on them. That would be violating the third law. Okay? If you're saying, well, the horse is able to overcome friction, well, to be honest, you're maybe getting a little closer, but that's not describing the flaw in this statement. How is it possible that if forces are always equal and opposite, you're able to start moving an object? Try pushing your desk. If you push your desk, by the third law, there's an equal and opposite force. Doesn't that cancel out? Doesn't that mean you can't move the desk? Well, that obviously can't be true, right? Because you can move your desk. We see, whether in real life or in movies nowadays, we see horses pulling carts. So there must be some remedy to this. The remedy is what's drawn right here. This is very misleading. This is implying that for this horse and cart, when there's a force this way, there's a force this way, they cancel. The third law, I'm going to go back to my definition. It's talking about different objects. When one object applies a force on a second, the second applies a force on the first. Really, this should be drawn like this. The horse applies a force on the cart, and the cart applies a force on the horse. These forces are not canceling because they are on different objects. That's the main solution to this problem, different objects. It is true that these forces are equal and opposite, and if the horse pulls more, the cart pulls more, but they are acting on different things. And so I'm going to go to one more diagram. Okay, there's kind of a lot going on here. The Newton's equal and opposite pairs, there's two of them. There's this one, when the horse is pulling on the wagon, so the cart, or the wagon, feels a force from the horse feels a force from the wagon. The reason the horse is able to start moving is because the horse is pushing on the ground. So the horse, I'm going to redraw this one, pushes on the ground like so. Maybe I should change colors, actually. The horse pushes on the ground pushes on the horse. It's a little weird. The reason you are able to walk is because you push back on the ground pushes forward on you. So in addition to these forces, which is all the horse was talking about, that's a funny sentence to say out loud, the horse is also pushing on the ground. There's a third law acting on the horse, and if there's like no friction or you have a nice smooth rolling wheel, there is no canceling frictional force, so the cart is able to accelerate. The main idea for this problem: forces don't cancel because of the third law. That is not true. This is incorrect, saying the forces cancel, because those forces are always on different objects. Okay, common misconceptions with the third law. Thanks for watching.